Okay, so this paper appeared in the June 2014 issue of Clinical Chemistry, and it's looking at the measurements of 8 common analytes and looking at standardization between 6 routine laboratory assays. So the proficiency testing has naturally gained a well-deserved position in the context of laboratory management. So it's an essential part of laboratory management. And then proficiency testing with commutable samples and high-quality targets is essential for assessing the accuracy of diagnostic assays and the interchangeability of generated results. Now, the intrinsic quality of an assay may be influenced by the lab that's using it, and therefore the assessment under routine conditions is essential. So there's been an interest in using samples that are serum materials that are commutable, meaning that they resemble real patient samples more closely. One of the problems is that a lot of EQA schemes continue to use highly processed samples. These are lyophilized, and they therefore are potentially not commutable. And so this limits the assessment of the EQA assessment of laboratory performance. So in this study, they have taken samples from donors, and they have measured a number of different analytes. And the survey was intended to use fresh samples and to look at how assays are performed by clinical laboratories and what standardization there was. So they looked at 8 analytes: creatinine, glucose, phosphate, uric acid, cholesterol, HDL, LDL, cholesterol, triglycerides. And so the question is, what are the special aspects of how this was designed, and how did they assess the data? So essentially they took 20 fresh frozen single donation serum samples, which was prepared according to CLSI guidelines. They took laboratories that were using homogeneous tests, and I'm sure everyone understands what that means. And they looked at all these various platforms, and as I said, those 8 analytes. And in their data assessment, they looked at those quality indicators, they looked at the target values and the limits. So the quality indicators that they looked at, that they applied for performance assessment, were the intra-assay imprecision, the combined imprecision, bias, and the total error. And they estimated this for both the peer group and the reference level by assessing the data against the peer group mean and the all method trim mean, respectively. And then they estimated the combined imprecision data, and they also assessed the assays for peer variation. So the question is, what are the main findings of the study, and what are the limitations? So the results were as follows. They found good performance for most of the assays except for HDL and LDL cholesterol. And the quality was sufficiently robust for performance in a daily lab context. In some assays, there was noticeable bias for creatinine, phosphate, triglycerides, and LDL cholesterol, and then the uric acid in the thermoscientific assay. And obviously, as you went low and high concentrations, there were more biases. And there was a lot of interlaboratory differences, which we'll look at now. So in this table here, the blue shows where the limits were violated. So we can see here which assays had problems, either with there's cholesterol here, creatinine on this platform, HDL cholesterol here, LDL, phosphate in this ortho platform, triglycerides here, and uric acid. So in figure 1, if we look at figure 1, we can see the assay bias, in other words, the percentage difference. So it's the mean of the peer group result minus the target value. So each platform has a color. So Abbott has a red diamond, Beckman blue square, Ortho black triangle, Roche yellow, Siemens red square, Thermo Scientific blue diamond. So if we look at cholesterol here towards this level, 200 milligrams per deciliter, we can see there's one outlier here. Creatinine, quite a few on this platform here, which is the red square, which is Siemens. Glucose over here, we see at the very low, at the low end, and then HDL cholesterol as well. So in this one here, we've got LDL cholesterol, phosphate, triglycerides, and uric acid. So if we look at this one here, the LDL cholesterol, you can see this. There's a problem with the Beckman assay. The Beckman and the ortho assays. So the ortho is the black triangle, and then the blue square. For phosphate, assay comparability is not bad, except for this one here, which is the ortho, the black triangle. For triglycerides, the results were very good, with differences within the optimal limit of 5.3%. And for uric acid, comparability was also very good, except for Thermo Scientific, which is the blue diamond. So you can see all these Thermo Scientific results out here compared to the group that's here. So table 2 shows the bias versus the AMTM, the trimmed means observed at the 3 concentrations for the 63 laboratories. The biases represent the combined effects of laboratory and assay. The interlaboratory differences observed here were particularly influenced by assay bias, and the laboratories with maximum absolute biases greater than 15% were regularly observed. And those are all the blue underlined results. So this is quite a big difference, and this led to differences of more than 30% in some instances between the laboratories. So this study was designed to test the different performance attributes of assays performed on modern platforms and in a clinical setting. And the important part of the study was the fact that they collected fresh samples. And then this allowed them to investigate the comparability of the assays between the different platforms. And basically, in figure 1 and 2, it showed that even for simple analytes, the standardization status of certain assays is still a matter of concern. And they had to exclude 3 methods from the trimmed means because of a significant bias: phosphates, triglycerides, and uric acid. And the data for one LDL cholesterol assay suggested a 15% bias. They found differences between the assays of up to 8% with creatinine and HDL cholesterol, and concentration-related biases. So what this means is that there's considerable calibration differences between manufacturers and assays. What they're also suggesting that by pooling their samples, they diluted matrix differences that may be present in individual samples. The triglyceride dispersion they attribute to potential glycerol contamination. So what the study shows, one of the things that it shows is that in terms of HDL and LDL cholesterol, they suggest that the assays have not reached the quality that we find in other analytes. However, these may also be affected by pre-analytical conditions, dyslipidemia and diabetes as examples. The manufacturer where the LDL assay had a bias of more than 15%, I think it was the Beckman, argued that it was sample freezing that may have confounded the performance. That was their reason. They do point out that the study had limitations. The small sample volumes that they obtained restricted the number of participants, and they could only get reliable statistics from 63 laboratories, and because they had to control the peer grouping so that to estimate the bias. The concentration ranges covered by the samples were small, so it means that at abnormal levels, low or high, there was very little data on what there was no data actually on how the assays would perform. Target values that were traceable to reference methods were not available for all the analytes. They assumed commutability of their samples, but they say there's no better alternative than the C37 CLSI protocol to collect large samples. Their study can also be questioned with regard to the target setting for bias and traceability assessment. Some people said that their reference targets for cholesterol were inappropriate because the assays were calibrated to the Abel-Kendall method, which deviates from GCMS. So in conclusion, the study provided reliable performance on assay and laboratory performance in daily practice. The results show that there's some quality within peer performance, but there's room for improvement at higher and lower concentrations. There's sample related effects with isolated cases where the assays were deviated between manufacturers. So what they're suggesting is that there should be a tightening up of external quality assessment, and there should be more education of individual laboratories and more emphasis on quality assurance. And so therefore the study shows that dedicated quality assurance surveys are a powerful tool to uncover and hopefully solve certain problems in laboratories. But these do not substitute for the routine quality assurance schemes, the conventional ones, but should be complementary to this. So in other words, we, in a sense, for example, NHLS should be sending samples to all laboratories, the same sample to all laboratories, and seeing what results they get back from each laboratory. And I think that could be an interesting survey, especially with looking at all of these common analytes. And so this is the final comment. There was an editorial that was written on this as well. We can go through this editorial quickly. Proficiency testing, as I've said, is also known as external quality assessment. Most use materials that are not commutable. In other words, they don't behave exactly like real patient samples, and we often draw conclusions from them. And often there are differences between peer groups comprising laboratories that use homogeneous systems. There are things called accuracy-based surveys, which use commutable materials and reference method target values. They're becoming more widespread. The problem with these, it's difficult to obtain enough sample to supply all the laboratories, because you're taking it's just a limitation of the volume of sample that you can get. And it's difficult to achieve the full concentrations of things, to mimic high and low, to mimic disease. And so in this issue, as is the paper that we've just gone through, they collected 20 single donor sera, they made aliquots, they kept them frozen, and they sent them to different laboratories. And basically the results show there's room for lots of improvement. And as the authors, we pointed out that there were limitations. The number of laboratories was small, the concentration ranges went very narrow. They used the all method trimmed mean rather than comparing it to the reference method. So this was the, this is the, sorry, I'm right in the middle of something. Another example he gives is that, for example, the use of the MDRD equation, the widespread use of these equations requires that accurate creatinine values be used. There's some cases, tumor markers and immunosuppressant drugs where you can't harmonize. So the paper that we discussed will not solve all of the problems we're facing in trying to achieve interchangeability and exchange of clinical laboratory results. So obviously we need to be able to do more to improve our results. They suggest by distributing a relatively small number of single donor samples to a small number of laboratories, one can determine whether those systems are accurate. So as good as conventional quality assurance schemes may be, we can do better for sure. Thank you for your attention, and that's the end.